Greetings everyone, my name is Hajar Al-Hattar and today I will be presenting our project Anheuser Busch Ethanol Desulfurization Team. This project focuses on improving the value of waste ethanol produced by Anheuser Busch. During the beer production process, waste beer is distilled to produce ethanol at approximately 199 proof. However, this ethanol contains high levels of sulfur compounds, which makes it unsuitable for reuse or resale. As a result, the ethanol is currently shipped off-site to Kentucky for sulfur removal, which increases both cost and efficiency. The main problem is that the presence of sulfur prevents the ethanol from being used as a valuable product. This creates both an economic and operational challenge since Anheuser-Busch is not fully utilizing a potentially profitable byproduct. Therefore, the goal of this project is to develop a process that reduces sulfur concentration to below 1 to 3 ppm, allowing the ethanol to meet fuel-grade specification and be reused or sold. For our proposed solution, two-stage desulfurization processes, catalytic observation followed by caustic scrubbing, and this process was using Aspen model optimized using DOE and JUMP for the process. And for our alternative solution was protein method which Anis will cover. This slide shows our overall project timeline for semester 1. We started with defining the problem and planning the project, then moved to researching and selecting the best desulfurization method. After that, we focused on process design, modeling, and optimization using Aspen and DOE. Finally, we completed economic, sustainability, and safety analysis and finished with the final design and presentation.
Hi, I'm Erica, and moving on to semester 2, we further optimized the catalysis scrubbing method and assessed the sustainability of the process and potential safety risks. We then calculated the techno-economics for the finalized design. Looking at the market research for ethanol, we are looking at a global market value of about $116 billion as of 2025, with fuel and fuel additives accounting for 44.5% of the market share. There is a growing demand for ethanol in the biofuel and alcohol industries. Some of the key players include companies in petroleum, biofuels, and renewable energy companies. The main barrier of entry for Anheuser-Busch is the low production level of waste ethanol, as this project only spans to the Fort Collins facility. The main global competitors include corporate giants such as ADM, Valero, and Poet, while our local scale competitor would be Front Range Energy, making it more viable for Anheuser-Busch to enter the local market instead of on a global scale. For our budget, Anheuser-Busch promised $2,000 for this project. Due to a lack of time and resources to do lab testing for the chosen desulfurization methods, the team has shifted to focusing on the theoretical stage in the design process this year. The team has not spent any of the budget and have no further spending plans.
Hi, I'm Anis. I'm going to go over the protein method. The protein method utilizes a mesh of de novo proteins in a plug flow reactor. The mesh of proteins will uptake the sulfur they are exposed to, which will then be removed when binding sites are full, and reused by flushing them with high-flow N2 and O2 as well as tris-hydromethyl-aminomethane to remove the sulfide compounds. The proteins can then be reused until the binding sites are no longer active. There were several proteins that were considered for this particular purpose. However, one MOH was chosen due to its strong affinity to sulfur, as well as its ability to release the sulfur under certain conditions. Further, while the protein is a biologic, it is highly unlikely to interfere with other organic mechanisms if released, which makes it the safest option for AB. We also considered 3 different processes depending on space in AB's facility as well as protein stability. Because there's enough space in the upstream facility, we decided on process B, which is the PFR method. This method significantly decreases the amount of ethanol the protein is exposed to, thus increasing the stability of the protein in the environment. Due to the novelty of the process, this has never been used in industry. However, there are several potential use cases outside of this project that have been examined in order to better design the protein. The use of this pipeline has been extended in pharmaceuticals, in which there are potential for use in drug discovery, targeting, and modulation. There is also ongoing research on using proteins as biological switches, as smart materials, or in biomaterials. In other words, there is a huge variety of industries in which this methodology is applicable. The diagram shows the process that was taken to get to the final protein. First, the stability of the protein was determined using GROMAX. This determines whether or not the process is even viable within the specified upstream conditions at AB. This was done using CU's HPC Alpine. Then, environments on the HPC were created for each of the following steps: RF diffusion 2, protein NPNN, and AlphaFold 3. The next steps would have been to validate the produced protein experimentally. The first model run was GROMACS to determine protein stability in the solvent. The main goal was to determine the project viability in AB's upstream conditions. This was done by approximating molecular motion through molecular dynamics software and energy minimization. The protein was simulated in a box of 10% ethanol with 500,000 time steps with a canonical NVT assembly. This produced a systematic approximation of the protein in AB's system. As seen in the graph, the protein is stable and the linear fit is close to horizontal. This fit was generated from the data produced in GROMACS by a MATLAB script. GROMACS also generated an approximation for binding kinetics, which was then used in a SuperPo model. The model shows that the protein is highly effective at binding in the sulfur and removing it from the environment. The second part of the protein design is to build a de novo protein that is capable of being a solid catalyst in the PFR. The purpose of these steps is to create a protein that is able to make a mesh by combining the binding protein 1-MOH to the two constituent proteins SpyCatcher-SpyTag. This beta-barrel alpha helix complex binds to each other irreversibly, which is used to generate the mesh. RF diffusion was used to create a full cysteine backbone for the complete protein, which binds 1-MOH to the SpyCatcher-SpyTag to make one protein. To do this, the protein has to be one chain with gaps for the linkers. Pymol was used to do this. Then, protein NPNN was run, which generates amino acid sequences designed to fold in 3D protein structure. This gives structure to the protein that allows it to fold. The final step is to validate the structure using AlphaFold 3, which produces the 3D structures and interactions. Overall, we ran thousands of iterations in over 25 designs. The best outcome currently has a PLDDT score of 85%, which is a per residue confidence metric used by AlphaFold 3 to estimate how accurately a protein structure approximates the true experimental atomic structure. This approximates how solid each residue is. Looking at the movie, we can see limited stochastic motion in the built sections, which gives good confidence that the protein would be stable in situ. Therefore, all model metrics show that the protein will be highly effective in AB's system.
I'm Bennett, and I'm going to be talking about our process description for our main method, which is the catalyst and caustic scrubbing method. This process will be ran continuously for 10 days per month with a flow rate of 170 gallons per hour to be able to desulfurize all 40,000 gallons per month and to minimize costs from labor and startup and shutdown costs. Our process begins with 199 proof ethanol from the feed tank and will then run through an 130-gallon PBR, a 25-gallon caustic scrubber, and will be pushed through with a pump with a capacity of 240 gallons per hour. And 2 PBRs are in our system to create redundancy and to mitigate time losses due to maintenance.
My name is Zach, and this shows our overall process synthesis for removing sulfur from the ethanol. The goal is to achieve low sulfur ethanol using a simple and cost-effective two-step system. First, the ethanol feed enters 2 parallel packed bed reactors. These reactors contain a metal oxide catalyst. In this step, the majority of the sulfur compounds like hydrogen sulfide, H2SO4, and sulfur dioxide are removed through catalytic reactions, forming stable metal sulfides. We use 2 reactors in parallel so one can operate while the other is regenerating, allowing for continuous operation. After that, the stream moves into a caustic scrubber. Here, a sodium hydroxide solution neutralizes any remaining sulfur species, essentially polishing the stream to meet our final sulfur specifications. Finally, the treated ethanol goes to the product tank. Overall, this system achieves near complete sulfur removal while staying compact and ethanol compatible. The key advantage is that we combine the high efficiency of catalytic removal with the reliability of a scrubber to ensure consistent product quality. For our optimization strategy, the goal is to identify which variables actually impact sulfur removal while maintaining ethanol purity. We tested temperature, reactor length, and catalyst loading, and found that temperature was the only significant factor affecting sulfur removal. This is important because it simplifies the design. We don't need to oversize the reactor or add extra catalyst. We can focus on just temperature control. Using this approach, we reduce sulfur from about 18 parts per million down to 0.024 parts per million while still meeting fuel-grade ethanol specifications. The key takeaways from our optimization study is that temperature becomes our key control variable, making the system easier to operate and more efficient. We're able to maintain ethanol at around 199 proof while achieving extremely low sulfur levels. Overall, this allows Anheuser-Busch to convert a low-value waste stream into a fuel-grade product, increasing its economic value.
I'm Bethany, and I'll be going over our process controls. So for our system, we care about controlling the temperature in our packed bed reactors, and we also wanted to control the pressure to avoid situations such as a runaway reaction. So in order to control the temperature and the pressure, we have control feedback loops, which you can see on the P&ID diagram shown on this slide. And using those control feedback loops, we can adjust the inlet flow rates and composition of the sulfuric ethanol that is flowing into each of our packed bed reactors in order to maintain those temperature and pressure set points where we want them in order to have the most optimal desulfurization system. Moving on from the packed bed reactors, we then are looking at our caustic scrubber here, and again we have a feedback control loop which is allowing us to adjust the inlet flow rates and inlet compositions of ethanol into our scrubber, where again we are wanting to control the pressure of that system in order to maintain the most optimal conditions for the sulfuric reactions so that our ethanol flowing out of the scrubber and into that final ethanol product tank is going to be the most optimally desulfurized ethanol. When conducting our safety analysis for this process, our team identified 20 hazards, and of those 20 hazards, 3 were classified as highest priority, and this is because they had both the highest likelihood of occurrence as well as the most severe consequences. And so after identifying those hazards as being the most severe consequences because they have risk of explosion and ignition, since we're working with ethanol, which is a flammable liquid, our preventative recommendations fall around eliminating the risk of ignition and explosions. So this looks like engineering controls included in our system. So we will be adding pressure release valves to our scrubber and our packed bed reactors to prevent pressure buildup within the system. And then we're also recommending a series of safety changes to the Anheuser-Busch facility, such as having some separation between the operator's control room and the process itself so that in the event of an explosion or accident, personnel will be safe.
Our team evaluated 7 sustainability metrics and identified the 4 most important for our process. These were environmental impact, strategic innovation, product stewardship, and value chain management. By evaluating these metrics, we found the following ways to maximize the sustainability of our process. For environmental impact, we found ways to use the waste responsibly by using the waste sulfur as fertilizer in the Anheuser-Busch farms. And Anheuser-Busch is committed to using 100% clean energy, so all of the energy used by our process will be clean. For strategic innovation, we found the ideal conditions for desulfurization in our process and researched the ideal catalyst to use. For product stewardship, we will find consumers that are both sustainable and close. And for value chain management, we decreased the driving distance and eliminated secondary processing that has unknown sustainability.
Looking at our techno-economics, you can see that first value there is our total depreciable capital. This was calculated based on the upfront equipment costs as well as the year 1 startup installation costs. And then from there we were able to calculate the annual sales and costs that will result from this process, which allowed us then to calculate earnings, cash flow, cumulative percent value, and then interest return rates. And you can see here that after a 1-year startup, Anheuser-Busch is projected to start having net positive cash flow off of this process. Based on our calculated cumulative present value and internal rate of return, this desulfurization process is projected to become net positive after 4 years, which means that after 4 years, Anheuser-Busch will be able to start profiting off of their ethanol sales. So not only is this allowing them to have an additional income stream after 4 years by selling the ethanol, this additionally benefits AB financially because it allows them to cut out the third-party company that they are paying to desulfurize their ethanol currently, and it also reduces shipping fees of having to send off that ethanol.
In conclusion, our project successfully developed a process to remove sulfur from waste ethanol produced by Anheuser-Busch. Starting with the process performance, we were able to reduce sulfur level around 18 ppm to below 3 ppm while maintaining the ethanol purity approximately 199 proof. This means the ethanol product meets fuel grade requirements and confirmed that our process is technically feasible. From an economic and sustainability perspective, the results were also very positive. Overall, our design provides a complete in-house desulfurization solution that converts a low-value waste stream into a valuable product. It's safe, practical to implement, and shows strong technical, economic, and environmental performance.